So last class we talked about the percent solutions, and we talked about the syringes and loading syringes and finding the scales. And that's one of those skills of determining those scales and what the divisions stand for that some people struggle with. So if you are, make sure you're putting in the practice and getting good at that so you can read those syringes. So the percent solutions, now remember we had three types. We had weight in weight, we had volume in volume, and we had weight in volume. And we said there was only one of them that was additive. The weight in weight was additive, where if we knew what the weight of the medication was, we could determine how much saline or sterile water that we had to add to that. The other ones, volume in volume and weight in volume, were usually not additive. Usually we combine them together, the total would be less than the two of them separately. The weight in volume is the most common that we will use usually it's a powdered medication. In some sort of a sterile water. And remember, use the abbreviation NS for neutral solution or normal saline. And usually, a lot of our medications will come in a sealed, sterilized vial. And many of them will already be constituted. And what constituted means is that, I gotta pause here so I can spell it, constituted, there we go. What constituted means is they already have the fluid added and they've already been diluted. But many times if you're shipping a high volume of this, the powder is very, very light compared to the whole solution. So they may ship vials that just contain that powder in it and no fluid. And you actually have to take a syringe before you use it and add the sterile water, the saline in there, and shake it well and mix it so that you can use it. And that's done, like I said, partly for shipping weight and also partly to keep the powdered medication fresh. So anyway, a lot of times you might read on a label it might say 600 milligrams of medication constitute to 120 milligrams per milliliter with 4.5 milliliters of sterile water. And again, that sterile water is just what we've been referring to as NS. If you do the math on this, 120 milligrams per milliliter and the fact that there is 600 total milligrams of medication there. So put the 600 milligrams on top. If you cross multiply and divide, 1 times 600 is 600 milligrams. Divided by 120 is 5 milliliters. That total solution should be 5 milliliters in order to contain that full 600 milligrams of medication. So where did the 4.5 milliliters come from? Remember we had talked about these weight and volume solutions. And if you are constituting them on your own, you're going to first put in the powdered medication into a beaker, and then you're going to have whatever level of fluid you need marked off or handy so you can check it really quickly. And then you are going to fill that with that fluid up to that level. And obviously you're going to fill it below that level and you're going to mix it. And you're going to keep mixing it as you fill it until you get up to that level. And that's really the only way in those weight in volume solutions to get the total volume correct. Because we don't know for sure how much saline, how much sterile water it's going to take to get that desired level. So on this vial, when it says constitute to 120 milligrams per milliliters with 4.5 milliliters of sterile water, because that's a sealed vial, we can't dump it out and and check to see how much water it takes to get to that desired level. So they have to tell us that it's going to take 4.5 milliliters of sterile water to constitute that, to get that to that full volume, so that 600 milligrams is constituted to 120 milligrams per milliliter. The reason I'm bringing that up is don't be confused by a label when it says something like that. The math does not work out, and we know it doesn't work out. It intentionally doesn't work out because the powder has some volume. So the 120 or the 600 milligrams of powder, I should say, is increasing that total volume by half a milliliter. So we would get the full 5 milliliters of volume. All right, so our new topic today, our last topic before we head off for a week off here, is going to be talking about dosage calculations. And dosage calculations have 3 different processes we can do. And I'm going to go through them in the order for me from my least favorite to my most favorite, the one I use the most. So my least favorite method, which it happens to be the one the book tends to stress the most, is the dosage calculation formula. The next one we'll talk, and notice I'm leaving a blank here because I'm going to fill in a couple of things here. The next one we're going to talk about after the formula is the proportion method, which is just ratios and rates within proportion. And then the third and final method is dimensional analysis. Dimensional analysis is just a fancy word, as we said before, for measurement conversion. The reason I left some space up here is I want to talk about some disadvantages and advantages possibly of each of these. For the dosage calculation formula, the big disadvantage is it can only be applied, it only applies to a narrow category of problems. So only applies for a few problems. So for different types of problems, you'll need different formulas. The second is it can only be used for one-step problems. For multiple step problems, it has to be applied repeatedly. So I mean, there are some problems where we might actually have to apply that dosage calculation formula 3 or 4 times to get to the final result. The pieces of that formula can be a little bit confusing, but once you know what those pieces mean and how to find them, it is relatively straightforward. You plug in the numbers and you crank through an order of operations calculation. The proportion, it applies to a wider scope of problems. That's an advantage. But, however, so I'll put that as a plus, it still is only able to be used on one-step problems. So again, if you have a multiple-step problem, it has to be applied several times. A second weakness of it is if it is a multiple-step problem, you have to decide which equivalency to use first. If it's a single-step problem, the proportion method is pretty straightforward. Dimensional analysis, I'm trying to think of any weaknesses of it, and I can't, but the major strength is it can always be used. It always applies. Now, to be honest, for myself, when I do these problems, I will often use a mixture of the proportion method and dimensional analysis method, because certain problems, at least certain steps within certain problems, it is easier to use that proportion than it is dimensional analysis, just because it fits right into it. So let's take a look at each of these methods. Let's look at our dosage calculation formula. The formula is D over H times V equals A. D stands for the doctor's orders. So that's the amount of medication the doctor is ordered to be given to that patient. H is the on-hand dose. V is what we call the vehicle. So the on-hand dose and the vehicle are usually related, and they both usually are found on the label of the medication. The on-hand dose is the dosage that's available within the medication, and the vehicle is what carries that on-hand dose into the patient. And as we look at some examples, they'll hopefully become a little more clear. And A stands for the administered amount. How much do you actually give to that patient? So let's look at an example. Let's say your doctor's order is 1,300 milligrams of ibuprofen. And you look at the label of the bottle, and the label is saying 500 milligram tablets. So if we look at our formula here, the first part, D, the doctor's order, is pretty straightforward. What is the doctor's order here? Go ahead, somebody be brave. Is that 1,300 milligrams? Okay, so now then, the on-hand dose is a little bit trickier. But the key to the on-hand dose is because they are in the same ratio together, the doctor's orders and the on-hand dose must have the same units. So since the doctor's order is in milligram, the on-hand dose here must also be in milligrams. So we have the 500 milligrams must be our on-hand dose. So remember we said the on-hand and the vehicle are linked together. According to this label, what carries that 500 milligrams to the patient? Tablets do. That's 500 milligrams per tablet. Or what that's really saying is 500 milligrams is equal to one tablet. And so that equivalency is what links the on-hand dose to our vehicle. So this is one tablet here. So our first step then to solve this, just order of operations, 1,300 milligrams times 500 milligrams. Milligrams cancel out. Did I say times? 1,300 divided by 500. The milligrams cancel out. 1,300 divided by 500 is 2.6. That is multiplied by our vehicle. So you see what always happens here is the units in both the orders and the on-hand dose cancel out, and the vehicle determines the units of what we administer to the patient. So 2.6 times one tablet is 2.6 tablets. Now something I should mention here, since we started talking about tablets a little bit, most tablets either are whole tablets or what we call scored tablets. A scored tablet is just a tablet that has a notch in it in the middle. So that's really, well, I'd say really easy, but it's easier to break in half. And you can break it in half relatively precisely. Very, very close to half the medication going either way. So 2.6 tablets would be almost impossible to do. If we had capsules, you could just divide up the capsules a little more precisely by dumping them out. But if it's tablets, we usually have to go to the nearest half tablet. Well, 2.6 is between 2.5 and 3, and it's obviously closer to which one? Two and a half tablets. Well, let's look at a slightly different example. Let's say our doctor's orders are for, have a good one, 280 milligrams of medication. Our label says we have 250 milligrams in 4 milliliters. So for our formula here, once again, the doctor's orders would be which one? Don't be shy. Perfect, 280 milligrams. What's going to go below it for the on-hand dose? The 250. The 250, good. Then our vehicle would be the 4 milliliters. Wonderful. That's always the toughest part is determining the vehicle in a lot of these. Remember, when you see this 250 milligrams in 4 milliliters, the way to interpret that is that 250 milligrams is equal to 4 milliliters. So then over here, the milligrams cancel out. 280 divided by 250 is 1.12 times our 4 milliliters. Well, 1.12 times 4 is 4.48 milliliters. So now going back to last class, depending on what we have for a syringe, that might be rounded to 4.5 most likely, depending on whether our syringe is capable of going to the nearest 500ths or to the nearest 100th of a milliliter or whatever it is capable of reading. So let's have you guys talk me through one here. We have our orders for 125 milligrams. Our label says 5 milligrams per milliliter. So what are we going to start out with? The doctor's orders of 125 milligrams. Perfect. What's going to go below it? 5 milligrams, and then times?
1 milliliter.
Perfect, 1 milliliter. When you see that, again, you interpret that as 5 milligrams is equal to 1 milliliter. So, the milligrams cancel out. 125 divided by 5 is 25. Times 1 milliliter, we would administer 25 milliliters to that patient. The weakness of the dosage calculation formula, I mean, you can see it's very straightforward once you figure out, what numbers really are which and how do you get information off the label to put into the formula. It's very simple and very quick to calculate. The weakness is when we run into things like this. Let's say our doctor orders, let's do 450,000 units of a medication. And on our label, it says 100,000 units in 1,000 milligrams. I'm just doing usually I would say 100,000 units per gram or in 1 gram. I'm putting 100,000 milligrams there to simplify it for us a little bit. And then maybe 25 milligrams in 2 milliliters. So for this problem here, we start out with the doctor's orders, the 450,000 units. What would our on-hand dose have to be? Well, it has to be units, right? It has to match the same label. So it's got to be the 100,000 units. Well, on the label of the medication, what does the 100,000 units link to? Perfect, the 1,000 milligrams. So now I'm going to do some dividing out of zeros here. I'm going to divide out by 10,000 here, get rid of 4 zeros there and 4 zeros here. So 45 divided by 10 is 4.5 times 1,000 milligrams is 4,500 milligrams. Well, we need to get to milliliters because milliliters is how we're going to measure what we give to the patient. So we have to go through this process one more time. Now, this isn't necessarily the doctor's orders anymore, but that is derived from the doctor's orders. So we start out with the 4,500 milligrams. And now we have this relationship of the 25 milligrams in 2 milliliters. So 25 milligrams is our on-hand dose, and 2 milliliters is the vehicle that carries each 25 milligrams into the patient. So milligrams cancel. We have 4,500 divided by 25, which should give us 180. Times 2 milliliters, we are going to administer 360 milliliters of that medication to our patient. So you can see that dosage calculation formula has a weakness there as we get to more complex problems, and we will see some that we have to go through 2 or 3 stages. We have to apply it 2 or 3 times. And remember, I said I simplified this problem here by using the 1,000 milligrams instead of 1 gram. That would have meant that we would have ended up with an answer here as 4.5 grams, and we would have had to have converted that because we don't have anything else on our label equating grams. We only have milligrams. So we would have had to have done a measurement conversion here from grams to milligrams before we could have done this second step. Our second method is the proportion method. Now, the proportion method is similar to what we could do if we're dealing with regular measurements. So let's say that we have 2.5 fluid ounces of medication, and we want to know how many milliliters that is. Well, we look up and we find that 1 fluid ounce is equal to 30 milliliters. So when we're using the proportion for measurement conversions and stuff, we start out with the equivalency. The equivalency is this: 1 fluid ounce equals 30 milliliters. It doesn't matter which one we put on top. So 1 fluid ounce over 30 milliliters. On the other side, then, we are going to compare the doctor's orders to the administered dose. So the doctor's orders here, we say the doctor's orders to the administered dose. When we're doing a measurement, we're looking at comparing the old value to the new value. Our old value that we're starting with is the 2.5 fluid ounces. That goes with the fluid ounces. We just put the values over here, matching up the units. So the bottom is going to have to be milliliters to match up. So we cross multiply 30 times 2.5 is 75. Divided by 1 is 75. So that is 75 milliliters. So 2.5 fluid ounces is equivalent to, or equal to 75 milliliters. So for our medical calculations here, our dosage calculations, we use that same relationship. We have an equivalency here. That equivalency generally comes off the label of our bottle. And then comparing old to new, as I noted here, we're comparing doctor's orders to the administered amount. So let's say we have orders to administer 700 milligrams of medication. And on our label, it says 200 milligram tablets. So remember, our equivalency comes from our label. We said that this label of 200 milligram tablets can be interpreted as 200 milligrams equals 1 tablet. That's our equivalency. Doesn't matter whether I put tablets or milligrams on top. I'm going to put the milligrams on top. 200 milligrams equals 1 tablet. On the other side, I have the 700 milligrams from the doctor's orders. That has to match up with milligrams. So now to find our missing number, we cross multiply and divide. 1 tablet times 700 milligrams is 700. Divided by 200 is 3.5. And this unit here must be tablets. If we use the units with this here, tablets times milligrams is a tablet times milligram. Then we divide by milligrams, so it'll cancel out the milligrams, leaving us with tablets. So we get 3.5 tablets. We might have orders for 275 milligrams of medication. And our label, 50 milligrams in 4 milliliters. Where would we start out with this problem? What's our first ratio going to be? Remember, that first ratio is the equivalency that comes off our label. That's going to be the 50 milligrams in 4 milliliters. So now what has to go on our other side? Well, the doctor's orders, perfect, 275 milligrams. Milligrams are on top here. Milligrams must go on top over here. Good job. So we know that our result's going to be in milliliters, which is what we want. Cross multiply and divide. 4 times 275 divided by 5. We divided by 50, but so it's 22 milliliters it comes out to be. So we would administer 22 milliliters of that medication to our patient. Now, as I mentioned at the beginning here when we were going over the 3 methods, the proportion method is also a little bit weak when we have multiple steps. So let's say the doctor's orders are for 250,000 units to be administered. And our label is 100,000 units per gram and 25 milligrams per milliliter. To use the proportion method, we start out with an equivalency off the label. But here there's 2 equivalencies. to figure out, so the first thing we have to figure out is which one we're going to use first. And so we do have to look up at the doctor's orders. The doctor's orders are in units, so we have to use an equivalency that has units in it. That's going to be the 100,000 units. Per gram in 1 gram. So on the other side, the doctor's orders of 250,000 units have to go on top. And we cross multiply and divide 1 gram times 250,000 units divided by 100 is 2.5 grams. Now there are actually a couple of things going on here. First of all, we need milliliters to know what to administer to the patient because we're administering this medication in milliliters. So we need to convert grams to milliliters, but we don't have an equivalency from grams to milliliters. The only equivalency we have to milliliters is from milligrams. So our second step here, before we can do that next piece, is to take that 2.5 grams and convert it into milligrams. Now, if you're familiar with the metric system enough, you can just move decimal points. Grams to milligrams, there's 1,000 milligrams in a gram. So just move the decimal point over 3 spots. So that's going to be 2,500 milligrams. So now that is, again, it's not the doctor's order, but that is derived from the doctor's order. So we start out, that's going to be our doctor's order for the next problem. We start out, since it's the proportion method, with the equivalency from the label, dealing with milligrams. Is 25 milligrams in 1 milliliter. Per milliliter is 1 milliliter. So on this side is 2,500 milligrams, and we will cross multiply and divide. 1 times 2,500 divided by 25 is 100 milliliters. So 100 milliliters would be administered to that patient. Okay, so to my favorite, dimensional analysis. As I said, this one is my favorite because it can be applied to every type of problem. Proportions can be applied to most every type of problem as well. But dimensional analysis can be used for every type of problem. And the beauty of it is you don't really have to know any formulas. You don't have to know anything about the medications. All you have to do is match up units. You know what we're getting rid of and what we need to convert to. So if you think of that example again of, I think we're going nuts here. There we go. 2.5 fluid ounces being converted into milliliters. We don't need to know anything about fluid ounces and milliliters. If we have that equivalence, 1 fluid ounce equals 30 milliliters. We can use this to convert. So we'll always start with the original amount, the given amount, which is the 2.5 fluid ounces. And we'll make it into a fraction by putting it over 1. And now we're going to use that equivalency here to do that conversion. Now again, we don't have to know anything about the equivalency of the units. We just have to know what the equivalency is. Here we got fluid ounces on top, and we're trying to get rid of those. So I have to put fluid ounces on bottom here, so they'll cross cancel. The equivalency goes from fluid ounces to milliliters, so the top will be milliliters. Now we can fill in the numbers. In the equivalency, it's 1 fluid ounce and 30 milliliters. So the fluid ounces cross cancel. 2.5 times 30 milliliters is 75 milliliters. And on bottom, we just have 1 times 1 is 1. So that is 75 milliliters. So the beauty of the dimensional analysis, we always start out with that initial amount. For medical cases, it will always be the doctor's orders that we start with. And from there, all we need to know is the equivalencies. We don't have to know anything about the units we're dealing with. So let's say our doctor orders let's see here. 400 milligrams of medication. And our label is 150 milligram scored tablets. That word scored in there implies that we're going to be rounding this to the nearest half tablet. So let's go ahead and do our dimensional analysis here. Doctor's orders that we start out with, 400 milligrams. We'll make it a fraction by putting it over 1. Now our equivalency here, remember this means 150 milligrams equals 1 tablet. So milligrams are here. To get rid of them, we're going to put milligrams on bottom. Has to be tablets on top. 1 tablet is 150 milligrams. So the milligrams will cross cancel. The only units we have left are tablets, which is what we want. So on top, 400 times 1 tablet is 400 tablets. On bottom, 1 times 150 is 150. And we divide that out. 400 tablets divided by 150 is 2.67 tablets. Now we said we're going to have to round to the nearest half a tablet. So if you look at 2.67, so here's 2 tablets, here's 3 tablets, in the middle here is 2.5. 2.67 is obviously between 2.5 and 3. What I usually do is I find the midpoint. We know the middle of that is 2 3/4, which would be 2.75. 2.67 is smaller than 2.75. So that's going to round down to 2.5 tablets. So this dosage would be 2.5 tablets. Okay, let's do a couple more examples here before we run out of time. So the doctor's order is for 1,200 milligrams of medication. And on our label, it is saying we have 20 milligrams per milliliter. So again, we start out with the doctor's orders. Yes, you have a question?
I have a question. When does this class end?
The last test. Our last class is scheduled for May 19th, I believe. Usually I do the last test, the class before that, so that'd be May 17th.
Okay.
And then that way we have a couple of days that I can get them graded and back to you. Or if you need extra time, you've got time to finish it up. And then you guys have time to do quick corrections on them too if you want to before we do final grades.
Okay, sweet. Thank you.
You bet. You're welcome. Okay, so then for this one here, we start out with our doctor's order again. 1,200 milligrams. Put that over 1 to make it a fraction. Now our conversion factor, again, that comes from the label. 20 milligrams per milliliter is implying 20 milligrams equals 1 milliliter. So we have milligrams here. We've got to put them on bottom to cancel them out. So milliliters will go on top. And I always fill in those units first. It just makes it easier for me to put them in the right spot, and it saves a lot of mistakes, keeps you from screwing them up. So 20 milligrams and 1 milliliter. So the milligrams cancel out. 1,200 times 1 milliliter is 1,200 milliliters. 1 times 20 is 20. And that should divide out, I believe, to 60 milliliters. 1,200 divided by 20. So we would administer 60 milliliters of that medication to the patient. Now, on the other ones, we've seen the weakness when there's more than one stage, more than one step. Dimensional analysis handles it just fine. So let's say our order is for 750,000 units of a medication. Our label says 200,000 units in 1 gram. And let's say that this is 250 milligrams in 4 milliliters. So we'll start out with the doctor's orders. Unlike the proportion, we don't have to try to figure out what to start with. We always start out with the doctor's orders. 750,000 units over 1. Now we have to get rid of units, so we know that whatever we use here, units are going to have to be on bottom. So what we have with the equivalency there is the 200,000 units in the 1 gram. So now the units are gone. Our label is now grams. So we want to get rid of grams. We're going to put them on bottom. We don't have an equivalency for grams. We have an equivalency for milligrams. So the first thing I'm going to do is change my grams to milligrams. 1 gram is 1,000 milligrams. So the grams are gone. And now I'm going to get rid of milligrams. I do have that equivalency, 250 milligrams goes to milliliters, so 250 milligrams to 4 milliliters. The milligrams cancel out, and now I multiply. Now all the examples I've done so far, I've just multiplied straight across. As we get into some of these longer problems like this, we run into the danger, there's a lot of zeros here. We run into the danger of the zeros giving us too many digits to exceed the unit limits of our calculator. So what we're going to do is we're going to do some cross-canceling. I can cancel out, let's do 4 zeros here. I'll cancel out 4 zeros there. Cancel out another 0 here and take one off the 1,000. 0 here and take another one off the 1,000. So what we have on top now is 75 times 1 times 10, which is 750, times 4 milliliters, which is 300 milliliters. On bottom, I have 1 times 2 times 1 times 25, which is 50. 300 milliliters divided by 50 is 6 milliliters. So you administer 6 milliliters of that medication to the patient. We will definitely start in with these again when we come back after break. That's going to be on the 27th. I realize Boston, you guys will be gone until the 3rd. So we'll be doing some review on the 27th, and on the 3rd we'll be doing a lot of examples that will help you review what you missed that week you were gone as well. But you do have those assignments. Now something I'm not going to spend a lot of time going over in the class here, but it is in the book, and you should take a peek at it. On page 150 in your book, there are some vocabulary and abbreviations. Things like IM and IV. IM means intermuscularly. IV means intravenously. PO means orally. Q4H means every 4 hours. Q2D means twice a day. So those things like that, those abbreviations, I'm not going to test you on them. It's not going to be on a test of, what does Q2D stand for or anything like that. But those, you will be reading some labels. Those abbreviations will be on there. Those abbreviations might be in some of the problems, so you do need to know what they mean. You don't necessarily have to memorize them because you will be allowed to use your book on the test, of course. But you do have to be familiar with them so you understand what they mean. Okay, so that wraps up today. So our homework to be looking at is page 153 through 154. 1 through 15. That is the vocabulary and abbreviations. So that's that stuff off of page 150. And then page 162 through 163. 1 through 23, the odd. And then finally, page 168 through 169. Just a review of those syringes, 1 through 19. Okay, so with that, that's it for today. You guys have a great weekend, and we'll see you in a little over a week. And from Austin, we'll see you in about 2 weeks. Just have a good day.